Now I'm going to talk about the general form for unity feedback. So if you remember when I talked about the proportional control system, the controller here is just a constant, okay? And in general, I could have another transfer function here. So here I have the plant, which I'm calling GP of S. So let's call the controller GC of S, okay? GC of S, GP of S. Here's Y of S, the output, and R of S, the reference or the input signal, okay? So I'm just going to follow the same rule we had before. So I'm just cascading GP and GC, and so I get Y over R is going to be equal to GP, GC, actually, can't be so fast, GP, GC over 1 plus GP, GC. Okay, so this is the general form for unity feedback with these two, with a series or cascade controller form. Okay, now if you look at it, this is a closed loop transfer function. And if you remember, right, the roots of the numerator are the zeros, the roots of the denominator polynomial are the poles. So if we look at the denominator polynomial, okay, we call this the closed loop characteristic equation. And that is 1 plus GP, GC. And so the roots are the closed loop poles. Okay? So in other words, if we want to understand remember that the poles of any transfer function determine the time response components. And so if we want to understand the time response components of a closed loop system, then we're going to look at this closed loop characteristic equation and find its poles. And they're not the same as the poles of the open loop system. So that's one of the cool things about feedback, is that we can use the controller to put the poles where we want them to be so that we get the desired time response. Okay? So let me do some examples of that to make it a little bit more clear. So the first example is, let's suppose I have a first order plant and a first order controller. Okay, so this is a little bit messy here. Okay, so if we notice, so there's a first order plant, first order controller, we have open loop poles at S equals minus P1 and minus P2, and K here is representing some gain that I can vary in the controller. Okay, so let's go ahead and write down the closed loop transfer function. For this system. So what I want you to do, I'm not going to draw the block diagram, but I want you to visualize. So here is the block diagram, GC followed by GP, okay, and these are the specific transfer functions that I'm using. So the closed loop transfer function, I'm going to call that T of S. That's equal to it's GP, GC over 1 plus GP, GC, and I'm going to skip the S's in there for now, okay. That's right, T of S is going to be equal to 1 over S plus P1 times K over S plus P2, divide by 1 plus 1 over S plus P1 times K over S plus P2. Okay, and now I can multiply by the denominators here. So I'm going to get K over S plus P1 times S plus P2 plus K. Okay, when I multiply by the denominators of the two transfer functions. And now I can see here, this is the closed loop characteristic equation. Closed loop characteristic equation. Sorry to be short, but it's going to be S plus P1 times S plus P2 plus K. And so when I multiply all that out, I get S squared plus P1 plus P2 S plus P1 P2 plus K. Okay? And so I can compare that to the standard form, which is S squared plus 2 zeta omega n S plus omega n squared. And so I can equate the coefficients, and I could see that omega n, I'll use a different color for this, the closed loop undamped natural frequency is going to be the square root of P1, P2 plus K. And zeta omega n, right? 2 zeta omega n is equal to P1 plus P2. Okay, so zeta omega n is 1/2 P1 plus P2. Okay? And so what you can see, I guess, one thing that you should conclude from this, we start with two open loop transfer functions. We have two poles, right? Because each one contributes one pole. So the open loop system is second order. Okay, the closed loop system also has two poles, so it doesn't change the number of poles. It's still second order, but the closed loop poles now have a different location. Okay, and in particular, I can use the controller gain to change the natural frequency, right? Because K, I can vary K, and I can choose omega n to be what I want it to be. But I actually can't do anything about the settling time, because zeta omega n, the real part of the roots, doesn't have K in there, right? So it's just governed by the open loop poles. Okay. Now let me do another example. So here I'm going to say GP is equal to K over S times S plus P, and GC is just a 1. Okay. And so now I'm just going to write down the closed loop characteristic equation. Well, that's 1 plus GP GC, and I set that equal to 0. This is how I find the closed loop poles. So I write 1 plus K over S times S plus P is equal to 0. And so I'm going to multiply by the denominator, and I get S squared plus PS plus K is equal to 0. So now the roots of this equation are the closed loop poles. Okay. So stability and negative feedback. Okay. So if you remember, if we have any time response, let's write it like this: y of s is equal to g of s times, in this case, I'll call it r of s. Okay. When we multiply this all out, we're going to get a numerator polynomial and a denominator polynomial. Okay. And whether this is an open loop or a closed loop system, the roots of the denominator polynomial determine the time response. So roots of d of s equal the poles, and they determine the time response components. And this time response will be stable, meaning it will decay to 0 over time, provided that those poles have negative real part. So y of t will decay to 0 if and only if the poles, actually I should write it all the poles, have negative real part. Okay? And if any pole has a positive real component, y of t will not go to 0. It will blow up, okay, over time. So if any pole has positive real component, the system is unstable. Whoops, I didn't mean to do that. Let me. The pen doesn't track very well at the bottom of the page. Unstable. Maybe I'll use a highlighter. So here we're calling this stable. So let's look now, just as a quick example then, let's look at our first order system with negative feedback. And I'm going to go back to the proportional control system. Okay, so this is the controller. Here's the plant. Okay, and you notice that the time response here is going to be governed by this open loop pole at s equals -2. And so the open loop response of this system would have a time component that looks like e to the -2t. In other words, there's a time constant, tau, which is equal to 1/2 a second. Okay, half a second time constant. Right? If we think about settling time, it's going to take about 4 time constants, so about 2 seconds for this thing to settle. Now let's look at the closed loop characteristic equation. Okay, so that's 1 plus k times 1 over s plus 2 equals 0. And so I multiply that out. I get s plus 2 plus k. There's a closed loop pole. S equals -2 plus k. Okay. So in particular, this thing is always stable because the pole is always less than 0. So it's always stable for k positive. Okay. For a positive controller gain, it's always stable because the closed loop pole is always in the left half plane. And the cool thing is that by making the gain larger and larger, by making k bigger, I can actually make the time response faster. Right? Because instead of having e to the -2t, I've got e to the -2 plus k quantity times t. And so I can adjust the time constant as I like using negative feedback. Okay? But now suppose that we put this thing into positive feedback. Okay? So same system, same proportional controller gain, same plant. Okay, but now I have a positive feedback loop. So it turns out that I could basically write down the closed loop characteristic equation in positive feedback. Well, instead of 1 plus GP times GC, I get 1 minus K. Okay, so all that happened is it changed the sign. Okay, so this is a positive feedback. Positive feedback gives us a negative sign in the closed loop characteristic equation. And so we can now write this as s plus 2 minus k equals 0. And so the pole is that s equals -2 minus k. And so this pole is in the right half plane,